this section, we're going to take a look at solving systems of 3 linear equations and 3 unknowns. The goal, it's stated in the title. We're going to solve these things. And you can extend the method I'm about to show you to 4 equations, 4 unknowns, and 5 equations, 5 unknowns. Although we have machines, we have computers do it for us when we get too many unknowns. In this first example, we're going to solve the system 3x plus 2y plus 3z equals 3, 4x minus 5y plus 7z equals 1, and 2x plus 3y minus 2z equals 6. By the way, what do we mean by linear equations when there's 3 unknowns? Well, any one of these equations graphs not to be a line, but a plane in space, in 3-dimensional space. A plane is like a tabletop, a flat surface, except that it has infinite length, infinite width, and no thickness to it. But how do you tell just by looking that it's a linear equation? For instance, 3x plus 2y plus 3z equals 3, this first equation, how do you tell that it's linear? Well, you'll see that the power on each variable is 1. As long as that's true, it's going to be a linear equation. And that's true for all 3 equations, in fact. So let me back off the view here because we're going to need some room. And I'm going to give you some steps to follow that will work on any system of 3 linear equations, 3 unknowns. You might have to make some adjustments depending on the system. Not all of the steps will always be necessary, for example. So here we go. Step 1, we're going to select 2 of the given equations and eliminate 1 unknown. In order to show my work, I'm going to label these equations. The first equation, E subscript 1. So just E1. The second equation, E2. And the third equation, E3. So you can select any 2 equations you want. I'm going to select, just for the sake of argument, E2 and E3 and eliminate the x. Well, it's not just for the sake of argument. It's a little bit easier to eliminate the x's in those 2 equations than in the others. And by the way, you don't have to eliminate x first. You can eliminate whichever variable is easiest. So make your life easy. If it makes a difference in other examples, eliminate whichever variable is easiest to eliminate. So I'm going to take E2 and E3, and in a sort of elimination type method, I'm going to eliminate the x's. So in order to show that work, I can do this. Look, if I want to eliminate the x's, I can multiply E3 by -2 so that I get the opposite of what I have right here. So in other words, I'm going to take -2 times E3. That's -2 times the third equation, and I'm going to add that to E2. And I'm going to use this sort of symbolism to show my work, or to show you what I'm going to do. And then I will actually show my work as well. So -2 times E3, just double everything and take the opposite. So you're going to get -4x minus 6y plus 4z equals -12. And then you're going to add it to E2, so I'm going to write E2 right below that. 4x minus 5y plus 7z equals 1. Make sure you copy everything down right. Add them all up vertically. 0x minus 11y plus 11z equals -11. Well, okay, I can't resist. Let's divide through by not 11, but -11. We'll trade 2 negatives for 1 negative if we do that. So if I divide through by -11, that's the common coefficient or factor in all of these terms. So -11, divide by -11, divide by -11, both sides, and you'll get y minus z is equal to +1. So that won't always happen that you can simplify the equation, but that's That's definitely a little bit easier on the eyes than the way it came out originally. So notice what we did in step 1. We selected 2 of the equations and we eliminated 1 unknown. Okay, so now on to step 2. In step 2, we're going to select the equation we haven't touched yet, the unused equation, and doesn't matter which one of the others, and we're going to eliminate the same unknown. So we haven't used equation 1 yet. And we're going to select one of the other 2 equations, and we have to eliminate the same unknown, which is x in this case. So I think it makes sense to use equation 3 because the coefficient is a little smaller. The coefficient of x is a little smaller. So I'm going to use E1 and E3 and eliminate the same variable. Okay, so think about it. If I want to eliminate the x's, I have 3x here, 2x here. The smallest number that both the coefficient of 3 and the coefficient of 2 divide into is 6. So I'll multiply through E1 by, say, 2 to get a positive 6x in this position, in the first position. And I'll multiply E3 by negative 3 to get a negative 6x in this first position. And then I'll add the results together. So again, to show my work, I'm going to take 2 times E1, and then I'm going to add that to negative 3 times E2, or just go minus. You don't have to go plus a negative. Just go minus 3 times E3. Okay. Or you could have said negative 3 times E3 plus 2 times E1. You'll see me do it both ways. So if I do that, okay, just double E1. That's easy enough. 6x. If you double the 3x, you get 6x, and then plus 4y plus 6z equals 6. And then we're going to take negative 3 times E3, so that's negative 6x minus 9y plus 6z equals negative 18. So just make sure you've tripled everything, and you have opposite signs, and you know you're good to go if that's the case. Now, I should have had a negative 18 here, so that's why I always double check. So negative, negative, positive, negative. Okay, add them up. We get, what do we get? We get negative 5y plus 12z equals negative 12. So look what's happened. After step 2, I've got another equation with the same 2 unknowns that I got in step 1. So we've reduced the given system to a system of 2 equations, 2 unknowns. Some books call this the reduction method. And now step 3, hopefully it writes itself. In step 3, we're going to solve the resulting system of 2 equations, 2 unknowns. Okay, so let's collect the 2 equations together. So we have y minus z equals 1, and negative 5y plus 12z equals negative 12. So what's the best way to solve this system? You could use either substitution or elimination. I'm going to go ahead and use elimination. I'm going to eliminate the y's here. I think it's pretty clear that we could multiply through the top equation by 5 to get a positive 5y in this first position, so that when we add it to the bottom equation, we'll get 0y. So multiply everything in that top equation by 5, and we get 5y minus 5z equals 5. Add them up. Let me scroll down just a bit. And we get, let's see, 0y plus 7z equals negative 7. Divide both sides by 7, We get z equals -1. And then remember, you can plug back into one of these two equations. The top one's easier, the original top one, that is. Plugging in for z right there to get y. And we'll have then y minus a -1 equals 1. Same as y plus 1 equals 1. Which means if you subtract 1 from both sides, you get y equals 0. So far we've got two solutions. Z equals -1, two of the three solutions. Z equals -1, y equals 0, and now we need x. So what should the fourth step be? So step 4, we'll plug these results, z equals -1, y equals 0, we'll plug those results into one of the original equations to solve for the remaining unknowns. Okay, so I've copied the equations right here. I'm going to plug in y equals 0 and z equals -1 into one of these equations, doesn't matter which one, to solve for the remaining unknown. That's step 4. So, okay, just the first equation I think I'll plug into. If I plug into the first equation, I'm looking for x. Remember, I don't have x yet. I'm going to plug in 0 for y. So plus 3x plus 2 times 0 plus 3 times -1 for z. I get 3, that's equal to 3. Okay, so that's 0, so I get 3x. That's a -3 right there. Equals 3, or 3x is equal to, add 3 to both sides. 3x is equal to 6. Divide both sides by 3, x equals 2. So we've got all three answers, all three unknowns. They're not unknown anymore. X, y, and z. So x is 2, y is 0, and z is -1. We write our answer, instead of an ordered pair, we write an ordered triple, alphabetical order unless you're told otherwise. 2, 0, -1 is the solution. It looks like just like the ordered pair notation, except there's an extra coordinate. And it is correct to call z equals -1 an extra coordinate, because if you graph those three original equations in space, wait a minute, how do you graph something in space? How do you graph a point in space, let alone an entire equation? Well, you need an extra axis. So not just an x-axis, not just a y-axis, but you need a z-axis that runs perpendicular to the xy plane. And if you graph the first equation, for instance, you get, well, this is part of the plane that you get when you graph the first equation. Just a flat surface in space. Here's the second equation in green, plane in green, and then the third equation. The point of intersection is in here somewhere. In fact, I actually plotted that as well. There's the point of intersection, and if we put in a grid, you can actually see that that point of intersection occurs at x equals 1, 2, y equals, you haven't gone over anywhere on the y, in the y direction, up or down from this perspective. And then if we change perspectives, you can see that z, it sure looks like z equals -1. So this intersection point is at 2, 0, -1. And in fact, geometrically, that's what a solution to a system of three equations, three unknowns looks like. It's an intersection point in space this time.